Hello everyone. In this lesson, we will discuss the operating conditions for the crude oil electric desalting process. The electric desalting unit is responsible for the entire process from crude oil entering the electric desalter to its exit, including operation and maintenance of the crude oil flow, fresh water flow, softened water backwash line, demulsifier line, and the ancillary equipment. The stable operation of the electric desalting unit is the prerequisite and guarantee for the safe and stable production of the atmospheric and vacuum distillation units. First, let's look at water droplet coalescence and settling velocity. Common methods in the crude oil electric desalting process include adding demulsifiers, adding water, and applying a high-voltage electric field. The purpose of these measures is to cause water droplets in the oil to coalesce, separate from the oil, form larger droplets, settle, and be effectively removed. The settling velocity represents the desalting efficiency. So, how can we increase the settling velocity of water droplets in oil? According to Stokes' law, the settling velocity V of a water droplet in crude oil can be calculated by the following formula, where V is the settling velocity of the water droplet in stationary oil, G is the acceleration due to gravity, rho W is the density of water, rho 0 is density of oil, D is the diameter of the water droplet, mu 0 is the dynamic viscosity of the oil. It can be seen that increasing the density difference between the two phases, increasing the water droplet diameter, and decreasing the oil viscosity can all increase the settling velocity. Next, let's discuss the factors influencing the settling of water droplets in electric dehydration. Firstly, the effect of heating on settling velocity. From the previous analysis, heating can reduce crude oil viscosity, promote water droplet coalescence, and increase water droplet diameter. Simultaneously, the density of water decreases less with increasing temperature compared to the change in crude oil density, meaning the water oil density difference increases. Therefore, heating the crude oil facilitates oil-water separation. This is the commonly used heated settling dehydration method. Of course, the temperature during heated settling dehydration cannot be too high. Otherwise, light components and water in the crude oil can vaporize, requiring the desalter to operate at very high pressure. Therefore, the general heating temperature is around 100 to 120 degrees Celsius, while heavy oil desalting can use 125 to 148 degrees Celsius. The second factor for water droplet settling is water droplet diameter. According to Stokes' law, the settling velocity is proportional to the square of the water droplet diameter. Therefore, increasing the water droplet diameter can significantly accelerate the settling velocity. In the crude oil desalting and dehydration process, the key is to promote water droplet coalescence and increase their diameter. Now, let's analyze the operating conditions for electric desalting. 1. Temperature control. Heating the crude oil significantly reduces its viscosity. This decreases the resistance to water droplet movement, increases their velocity, and increases the chances of collision. This not only increases the tendency for coalescence, but also significantly speeds up the settling of larger droplets. Additionally, the solubility of certain emulsifiers in the crude oil increases, causing the emulsifying film to break spontaneously. All these factors favor crude oil demulsification and the removal of water and salt. However, beyond a certain temperature limit, the interfacial tension at the oil-water interface decreases, electrical dispersion intensifies, reducing the critical water droplet diameter and thus the settling velocity. Especially when using water-soluble demulsifiers, their effectiveness drops sharply when the temperature reaches the cloud point. Therefore, the oil temperature for electric desalting must be selected rationally, considering technical and economic indicators. Generally, the electric desalting temperature increases as the crude oil density increases. Typically, the heating temperature for electric desalting is around 100 to 120 degrees Celsius. 2. Pressure control. The electric desalter needs to operate under a certain pressure to prevent the vaporization of water and light components in the crude oil, which would cause agitation in the oil layer and affect water settling and separation. The operating pressure depends on the content of light fractions in the crude oil and the heating temperature, generally between 0.8 MPa and 2 MPa. 3. The role of water injection and mixing in crude oil electric desalting. Injecting water into the crude oil entering the electric desalting unit aims to dilute the salt concentration in the inherent water of the crude and dissolve crystalline salts in the oil, while also increasing the water droplet diameter. When the water content of the desalted crude meets the specified index, this can greatly reduce the salt content in the treated oil and improve the desalting efficiency. Water quality requirements for injection include 3 indicators: salt content, oxygen content, and pH value. High salt content in the water is detrimental to crude oil electric desalting. High oxygen content in the water can easily cause corrosion of the equipment itself. If the water pH is above 8.0, it can convert organic acids like naphthenic acids into active emulsifiers, intensifying emulsification or causing oil carryover in the effluent water. Whether the injected water can be fully dispersed and uniformly mixed with the crude oil greatly affects the desalting efficiency of the electric desalting unit. Insufficient mixing intensity means the water is not fully dispersed in the oil, and water injection fails to achieve the salt washing purpose. However, if the mixing intensity is too high, it may cause over-emulsification of oil and water, not only increasing energy consumption but also reducing the effectiveness of dehydration and desalting. Generally, it is appropriate to control the mixing so that water is dispersed into small droplets of about 30 microns. 4. Demulsifier adjustment. The demulsifier is one of the most critical factors affecting the desalting rate. In recent years, with the development of new oil wells, the impurities in crude oil have changed significantly, and the quality requirements for feedstocks in the petroleum refining industry have become increasingly higher. In response to this situation, many new broad-spectrum, multifunctional demulsifiers have been developed, generally composed of 2 or more components as compound demulsifiers. The dosage of demulsifier is generally between 10 microgram per gram and 30 microgram per gram of crude. 5. Electric field gradient control. Electric desalting requires the action of a high-voltage electric field. The voltage per unit distance is called the electric field gradient. A higher electric field gradient generally leads to better demulsification. However, when the electric field gradient is greater than or equal to the critical dispersion gradient, water droplets undergo electrical dispersion, causing the already coalesced larger droplets to break up again, reducing dehydration and desalting effectiveness. The actual strong electric field gradient used in various refineries in China is 100 to 500 volts per centimeter, and the weak electric field gradient is 150 to 300 volts per centimeter. In summary, to achieve the best electric desalting results, it is necessary to comprehensively consider the characteristics of the above factors. They each have their specific contributions to the electric desalting process, but also certain constraints, and they interact and complement each other. Only by reasonably coordinating and controlling the various operating parameters based on the actual situation can the desired goals be achieved. Alright, that concludes the content on the operating conditions for the crude oil electric desalting process. Goodbye, students. See you in the next class.